All right, everyone, welcome to chapter 19. This is the final chapter in the book and thus the final chapter in the course. Congratulations making it this far. Just push through this one and then we'll be all set to take the final. Your reading is listed here. Make sure that you're doing that. And the feature of this chapter is that we're going to be putting together everything that we saw from the last chapter and extending them out to real life situations. So let's dive right in. Okay, the two topics we'll be covering today are the pre-equilibrium approximation and catalysis. Let's talk about the pre-equilibrium approximation. So in this approximation, we're going to consider the following reaction. A reacts with B, and then it goes forward at a rate constant Kf to form I, which stands for intermediate, and then I can degrade back down to A and B at a certain rate constant K reverse. But I can also move forward and form products. This is a very common reaction mechanism, especially in biochemistry. Especially with regards to second order reactions involving enzymes and such. So what is happening here? We're going to assume that this step right here is slow and that both of these steps are relatively fast. So if we consider a reaction landscape again, where down here is the reaction coordinate or the reaction progress, then obviously over here we'll have the products, and over here we'll have the reactants, and then over here we've got some sort of energy. Then we'll have that plateau again where there's A and B, and then it's going to have to go uphill a little ways to get to that reaction intermediate I. But then there's going to be one more barrier that it has to cross before it comes down here to the products, like that. And so as the systems are bouncing around randomly, they're coming back and forth between A and B and also I at a pretty fast rate. But then it's a lot slower for the I to get over that boundary there and fall down to the products. So P is formed only occasionally, all right? And the reason why it's called the pre-equilibrium approximation is because these two steps to the reaction, from the products to the reactants to the reaction intermediates, is in equilibrium. Okay? And we can take what we learned from reversible reactions and we can use detailed balance. Hopefully you remember that from the last chapter. Detailed balance requires us to first write down the equilibrium constant. So we have products for this particular step over reactants. And this is a concentration equilibrium constant, which, if you recall, is the rate constant in the forward direction divided by the rate constant in the reverse direction. And if we just rearrange this equation algebraically, and we can multiply things on the denominator here over to this side, and we get that the concentration of the intermediate equals the rate constant times the concentration of the reactants. All right. And if we take a look at this second step of the reaction, I going to P, then that's going to allow us to write a rate law, and the rate law is just going to include the reactants in this case. So the rate of product formation with respect to time is going to be equal to Kp times I. But we know what I is right there, so we'll just plug that in and we'll get a rate of the reaction equals Kp times Kc, concentration of A, concentration of B. And we can expand out the meaning of that equilibrium constant and get Kp, Kf, Kr, concentration of A, concentration of B. So as you can see, this reaction overall is second order. And you may encounter some other types of reactions, in which case you would just have a different proposed mechanism, and you would use the principles here to figure out the proper way to use the pre-equilibrium approximation along with detailed balance in order to get the final rate law.